We've spoken about batteries before on the show. Dr. Euan McTurk, battery electrochemist, came on and gave us chapter and verse on caring for batteries, how to properly charge a battery, and we dispelled a couple of myths about batteries. Now, that was almost 3 years ago. And while his thoughts about battery care, shadow mode charging, and whether lithium-ion batteries do explode as often as the media would have you believe haven't changed, the battery market has. Now, today, I want to look at battery design, touch on topics such as solid-state batteries, different battery chemistries, and what difference something as simple as a battery anode material can make to the battery itself. So welcome to the Future of Batteries episode. Hi, I'm Gary. This is EV Musings, a podcast about renewables, electric vehicles, and things that are interesting to electric vehicle owners. If you want one of these mugs, let me know. We'll see whether we can put some together. Now, before we get into the main bulk of the episode, can I ask a small favour? A like, subscribe, or a comment would be most appreciated if you found this episode useful. The EV Musings podcast is sponsored by ZapMap, the go-to app for EV drivers to find and pay for public charging with confidence. As an electric car driver, you're probably going to be acutely aware of your battery. If you listen to the naysayers, they'll tell you it's going to either burst into flames, run out of charge, die after about 3 years, or all of the above. Now, whilst none of that is accurate, there is a case to say that what your battery is made from and how it deals with things such as charging, heat, and cycling is something quite important. So it's one of those things of which is always interesting to be aware. Now, before we go much deeper into this, let's just look a little at battery basics. At the most simple level, a battery is a device which causes electrons to flow between 2 points. This flow of electrons causes a current, which in turn creates electrical power. In most batteries, you have 3 different physical parts. There's the anode, the cathode, and the electrolyte. The anode is the positive terminal of the battery, the cathode is the negative terminal of the battery, and the electrolyte is the medium through which the electrons move. Throughout the years of battery development, the trick to getting better batteries has been to modify one or more of these 3 components, and this is usually known as altering the battery chemistry. Back in time, the predominant chemistry was lead acid. Then we moved on to zinc carbon as a battery chemistry. This had a zinc anode and a carbon cathode. Ammonium chloride formed the electrolyte in a paste form, i.e. not completely liquid but not totally solid either, and we'll come on to solid-state batteries in a moment. Then we moved on to this breakthrough tech, which was lithium-ion. And what this meant is that the anode is made from graphite or carbon, the cathode from a metal oxide such as lithium cobalt, lithium iron phosphate, or lithium manganese oxide. The electrolyte has various compounds, but the salts used in it is something usually such as lithium hexafluorophosphate. Now, this combination of different compounds creates a stable battery that has a good energy density and can be cycled, i.e. charged and discharged, many times without a big loss of capacity, the so-called degradation. Now, you've probably heard about solid-state batteries as well. They seem to be the holy grail of battery tech at the moment. The main difference these have to the current crop of batteries is that the electrolyte in the middle is not liquid or aqueous. It is, solid. But looping back to the anode and cathode, these are the 2 main areas in which innovation and progress can be made with batteries. But with all these different battery chemistries, there's always a trade-off. Cobalt in batteries is something of a hot topic amongst those who want to find a stick with which to beat EVs, for example. Cobalt is generally used in the anode alongside lithium in the lithium-cobalt chemistry, but there are new chemistries coming out which don't use cobalt, lithium iron phosphate or LFP for one. And what it's worth remembering for different chemistries is that there's always a trade-off to be made when altering the chemistry. So as an example, LFP doesn't have as high an energy density as lithium cobalt. This means an EV with a similar size battery won't travel as far. But the upside is that LFP batteries can be charged to 100% and kept there with no adverse effects. Now, I could go on for a while regurgitating stuff from the internet about batteries, but I think the best way to look at things is to get our favourite battery electrochemist, Dr. Euan McTurk, on to give us chapter and verse. Now, we'll look at BYD's Blade 2 battery, at the donut, solid-state battery, sodium batteries, carbon batteries, air batteries, etc. Now, Euan does go into something of a 3-letter acronym frenzy at one point, so I've added in a glossary of terms to the show notes. So, good morning. Can I ask you to start by introducing yourself and tell the people where they might know you from, where you work, what you do, please?
Hi Gary, I'm Dr. Euan McTurk. I'm a Consultant Battery Electrochemist from Plug Life Consulting, and I work on anything technical, strategic or public outreach to do with battery electrochemistry, EVs, charging infrastructure and static energy storage. And you may have seen my YouTube channel, Plug Life Television.
I want to chat with you today about where the battery market is going in terms of innovation. Now, for years we had lead-acid batteries and a few slightly esoteric chemistries around there. Then we seem to have settled on NMC chemistry with the advantages and disadvantages of that. And more recently, LFP has come out as a chemistry of choice for many EVs, mainly due to the safety issues and the fact that you can charge it up to 100% without any problem. But from time to time, we hear of other chemistries that might be coming forward. Now, many of them are not necessarily intended for electric vehicles, but I want to have a bit of a discussion about them anyway. So, sticking with lithium-based batteries, we have lithium manganese oxide. Is it Spinel? Spinel?
Yeah. So you're looking at kind of lithium manganese rich or LMO, and that LMO has been around for a while. The initial kind of versions of it in power tools. Part of the problem is that the cycle life on it was typically quite short, and that's why you never really saw it in electric vehicles. But the likes of Ford and GM, it seems to be quite popular amongst American automotive OEMs, this chemistry, because they're used to NMC, and lithium manganese rich has similar kind of properties in terms of voltage and so on. It's a bit of a drop-in solution without necessarily having to overhaul the battery management system and the wiring thereof. But yeah, you are displacing expensive nickel and contentious cobalt, which is also expensive, with cheaper, more abundant manganese. The issue has been getting the cycle life up. That has now seemingly been achieved by GM and Ford, and I suspect that the US market will go fairly big on lithium manganese rich because there is this push towards stupidly high range, because Americans and Canadians drive stupidly long ranges because they don't have a decent public transport system. So, as you are pretty much entirely dependent on your car, you want that to be able to go as far as possible, and that's where, that's how they will get to their sort of 400 plus mile pickup trucks and stuff like that. I can't see that being of as much interest in Europe, where there's going to be the push towards LFP for cost, and also because the range has managed to improve through clever packaging, moving from cell to module to cell to pack and then cell to chassis designs. But with LMFP, the likes of the BYD Blade 2.0 coming on the market, we will start to get reasonably close to the same kind of energy density as NMC. Not quite, but more than good enough for European EVs and their range. So, that easily covers the UK market, French, German, Norwegian, all the kind of key cases. Interestingly, with LMFP, there's a UK company called Integrals Power that has demonstrated their LMFP cell and its ability to withstand very cold temperatures that would be the equivalent of Norwegian winters and so on, whilst retaining something like 80% of the capacity of the battery. Whereas LFP, conventional LFP, you'd be down to about 60% of that capacity at best, unless you've got really good thermal management systems in there. So LMFP could be a game changer for Northern European chilly winters, and quite frankly, if the Gulf Stream stops, UK winters as well. So, that's important for us. But when you look at the US, the focus seems to be on lithium manganese rich, because you are maintaining the exact, almost the exact kind of energy density that you would get out of NMC, but you're just making it cheaper to manufacture, and you've got less reliance on, chemicals, raw materials coming from contentious nations and supply chains and so on.
So the one which I think is almost not identical, but it's very, very close, is lithium titanate oxide. What's the subtle difference? What are the pros and cons? What would the market be for that?
So lithium titanate has actually been around for quite a while. Toshiba was one of the first to commercialize this with their SCIB battery back in the early 2010s. And the Mitsubishi i-MiEV that you might remember, one of the first EVs, modern EVs in the UK, over in Japan, there was an optional lithium titanate version of that. The range was less, but the lifespan was stupidly high. So I'm pretty sure that any of those that were sold in Japan will still be running around with a perfectly healthy battery in it. That cannot necessarily be said for the ones that used the earlier conventional lithium-ion cells, certainly the ones that were made pre-2012. were known to degrade a bit faster than the ones that had a subtle upgrade in their battery chemistry after that. But lithium titanate, that is not a change in cathode chemistry, positive electrode. It's a change in anode chemistry, the negative electrode. So instead of removing NMC, you're keeping NMC typically, and you are replacing the graphite with lithium titanate. It's a completely different structure from graphite, and it allows lithium ions in and out of it very quickly with minimal expansion. And as a result, you've got very low internal resistance. You've got good C rates, at least 4C, so you could charge the thing in 15 to 20 minutes if the car was capable of it, if the power electronics and what have you were capable of it. So yeah, quite impressive in that sense. There's another clever trick up its sleeve. Because it doesn't expand or contract much, it doesn't physically break itself apart. So the cycle life is, in some cases, over 20,000 cycles in comparison to what would have been about 2,000 cycles for conventional lithium-ion cells back then, although they're starting to improve today. But the other clever trick about NMC is that the actual anode structure itself acts as its own internal fuse. So if you were to do puncture with a steel rod or something, one of these kind of puncture tests, penetration tests on an NMC cell, you probably wouldn't be looking at much, because the area of the lithium titanate around that metal short circuit changes from a highly conductive phase to a highly insulating phase and acts as its own fuse. So it vastly slows down the self-discharge. So I've seen videos of crazy people in back gardens and stuff who've taken like an NMC cell, an LFP cell, and a lithium titanate cell. And, they've done the puncture tests, they've done the flamethrower tests, they've done all sorts of nuts things to them to really abuse them. And of course, the NMC cell is a bit theatrical about it. We know this. Conventional graphite NMC is quite blowy uppy if you are determined enough. LFP, there might be hot gas vents from it, but it's generally a lot safer. And then NMC, nothing much happens. I mean, you can get them to catch fire if you are determined, but I can get my office desk to catch fire if I'm determined. So, it's not going to blow itself up unless something catastrophically went wrong. So, lithium titanate, LTO, the market for that in EVs, the IMEV, as far as passenger cars go, was the exception that proved the rule. There was also the short-lived concept of the Lightning GT sports car in the UK. They talked about using titanate cells, but they never really got off the ground. Where we're starting to see titanate being used, because the energy density is much lower than for NMC and lower than for LFP, because the potential of titanate anodes is 1 volt higher than graphite. So you've instantly reduced the cell voltage. And because, as I'm sure we've discussed before, energy in watt hours is equal to voltage in volts multiplied by capacity in ampere hours. If you reduce the voltage, you reduce the energy, you reduce the range. So these are going to be in niche applications. They have sometimes seen use in electric city buses that have pantograph chargers at each bus stop, because they're able to charge up so quickly, but it's a fairly short range. So it poodles along to the next stop, charges for a few seconds, poodles along to the next stop. That's where it makes sense. I believe that, in fact, rail applications are starting to use this as well. If you look at the likes of Stadler, who make loads of different rail traction, whether it's massive locomotives for hauling loads of weighty freight and so on, or whether it's the multiple units that are used for commuter services and things. I've seen the kind of industry rundown of who's using what, and I swear there's someone in the board of Stadler who's like, how about this little electric commuter train, LTO? How about this big meaty freight train, LTO? And they're just like, we know it works, we know it's safe, we know it's long lasting, we'll just use this. But what about the range, sir? Oh, who cares, LTO? And that's what they're doing. But, so you'll find that the range will be comparatively limited, but the lifespan will be excellent. But where it gets interesting is that LFP is starting to equal the lifespan of LTO, but with improved energy density. You look at CATL's electric bus battery, which can do, it's LFP. I've forgotten what the energy density is, but you'll get more range out of it than an LTO battery. And the warranty for that is 15 years or 1.5 million kilometers, which is almost 1 million miles. That is a much cheaper chemistry, and it's very long-lived. So one would argue that LTO's days potentially could be numbered in some of these applications. They will inevitably continue to see niche use, but it's genuinely, it's a bit like the old hydrogen's the future because it can do this that batteries can't, that conventional batteries can't, but conventional batteries very quickly caught up with hydrogen, and the noose is very much around the neck of hydrogen. batteries like LFP, LMFP, and to an extent NMC, graphite, are starting to kind of circle around LTO and really limit the number of applications that uses, or that's used in.
Can we do a quick sidebar here? Because I know when we talk about battery chemistries, and you've thrown around a lot of TLAs, a lot of three-letter acronyms.
Yeah, so
every combination of elements that you put in, or compounds that you put into battery, will give you, there is always some sort of trade-off that you're making in some way, shape, or form. Do you want to give like a quick sidebar about what the potential trade-offs are? Not for every individual chemistry, but, for certain types of batteries, as you said, you might have longer range, but shorter cycles. You might have a higher fire impact. What are the general trade-offs that you make when you're designing a battery?
So, yeah, I mean, there are numerous factors to consider. Cost is a key one these days, especially for the automotive sector. And if you use cheaper materials, then you're going to get a cheaper battery, but you're probably going to get less range per charge. Safety is a key one as well, where if you tend to use more docile materials, you either end up with, in fact, no, you do tend to end up with reduced energy density, so reduced range, because that would either be your lithium titanate or your LFP, which should be considered safer, but they both have lower energy density. If you want stupidly high performance, you're typically trading lifespan for that, although we're starting to see some batteries that might buck the trend on that through incredible molecular scale engineering like the Blade 2.0, which is pseudo-affordable at least. The lifespan seems to be reasonable. It doesn't reach the lofty heights of lithium titanate or some conventional, long life LFP, but it's still respectable lifespan for a car. The chassis should be starting to rust through before those cells fail, but you've also got stupidly high performance. So yeah, that's starting to change. But the general rule was that high performance equals shorter lifespan, and that lower cost and improved safety equals lower range. But that's starting to change now with new chemistries that are on the horizon, and some that are already in cars today. And what's interesting is that there are a lot of new chemistries on the horizon. We're starting to see a great diversification of chemistries. If we look at EVs in the mid to late 2010s, pretty much all of them were using NMC, and that wasn't particularly exciting. Yes, there'd be differences within the cells, but it was fundamentally the same chemistry. Early 2020s, LFP starts to come to the fore in Europe and the USA to an extent, and now it's playing a huge role in Europe, thanks to predominantly Chinese manufacturers, either of cells or of complete cars. But we're starting to see new chemistries like sodium-ion, like lithium sulfur, like silicon anodes within lithium-ion cells, solid state, semi-solid state, etc. A lot of these have trade-offs of lifespan. And, we've been able to demonstrate significant improvements in energy density for the use of silicon anodes or solid state cell architectures and so on. You can talk about kind of doubling the range of an EV, etc. But lifespan is one of the issues that we're facing at the moment, and it needs a bit more development in the lab to get lifespan up from hundreds of cycles to thousands that you would need for a car. But such are the turbulent times that we live in that the startups who are manufacturing these next generation cells have pivoted away from automotive towards drone batteries, because funnily enough, there's a lot of militaries out there, particularly in the US and Europe where a lot of these startups are, who are keen to use local supply chains for strategically important reasons. And when it comes to, the performance of those batteries, they need as much runtime as they can get out of them. But because they're military drones, they don't often expect them back. So it's actually, it's also a really high markup that these startups can make off of it because it's a military application. Whereas automotive, they will really try and keep those margins low. A lot of these startups can charge pretty much what they want to stick these batteries in military drones. So, yeah, a clear ethical dilemma for these startups who would struggle if they were to see their batteries through to automotive scale readiness, commercial readiness. But this is actually giving an opportunity to be a kind of a living lab, a rapid prototyping of these incredible new chemistries, which will hopefully eventually reach the stage where they are doing thousands of cycles and are doing good things, ferrying people around in cars and buses and ambulances and other things that are positive for society.
Talk to me a little bit about, you mentioned them a few moments ago, they're sodium batteries. I think 11 labs, somebody who've put together a working version of this. What's the pluses and minuses of sodium batteries?
So there's 11 E's and then there's 11 energy, confusingly, and it's 11 Energy who are making sodium-ion battery energy storage systems. And what they're doing is they're using cells from Hina, or Hina, H-I-N-A, bought in from China, but they're assembling the battery pack in the UK. So Hina's been around for a few years now, and there was a city car in China that was launched that used their cells. So those are one of 3 families of sodium-ion chemistries. Just like with lithium-ion, sodium-ion is a broad church of chemistries. But what you're fundamentally doing is you're replacing lithium ions with sodium ions, which are bulkier, heavier, but more abundant and cheaper. So you get a trade-off in energy density, but in theory, once you are producing these at the same scale as lithium-ion cells, you are vastly reducing the cost. Sodium-ion has a couple of advantages. First of all, you can use cheaper materials in those cells. So, for example, the layered oxide version of the cathode, which is what 11 Energy is using, and it's what Naxtra, which is the CATL sodium-ion brand, is using in the latest generation of sodium-ion batteries in electric cars in China. So layered oxides have the greatest energy density. They are closest related to the likes of NMC that you would use in lithium-ion, but there's no cobalt. There's generally not nickel, although there can be. Depends on how determined you want to be to take a retrograde step. But you're generally using cheaper materials, and the lifespan is reasonable. The fact that Naxtra's managed to get layered oxide to do 10,000 cycles, which is probably double what you would expect out of NMC today, that's impressive. The energy density on that is almost similar to what LFP was doing maybe 5 or 6 years ago. So it's not too bad. Actually, it's probably maybe a decade ago, but it's still pretty decent. But sodium ion generally has lower internal resistance, lower cooling requirements, which means that you don't need as bulky a thermal management system, which means you can accommodate more cells in the space where that thermal management would have been in the battery pack. You also don't need to use copper for the current collector for the negative electrode. You don't need to use graphite. In fact, in theory, you can't use graphite. If you're determined, you can. But in theory, it's easier to use disorganized hard carbon because sodium ions are, in theory, too big to smash their way in between the layers of graphene that make up graphite. So you would just end up wrecking those particles pretty quickly. But anyway, so because you can use more abundant materials, you can use bio-derived disorganized hard carbon. So in other words, plant waste and so on. Like wood waste, etc. You can use those to make these incredibly ethical anode materials, and then you don't need expensive copper to paste that onto. You can use aluminium because sodium doesn't alloy with copper like lithium does. So that means you've got a lighter current collector material, a cheaper current collector material. You've reduced your costs. You can also completely discharge sodium-ion cells down to 0 volts, which you wouldn't realistically do in an electric car, but when it comes to shipping them from the factory to wherever they need to be, you can literally put a resistor across the terminals and you'd have 0 energy left in them. There's no way, even if you punctured them, they're not going to catch fire or anything because there's no energy left to have that rapid self-discharge. So that means there's not as much complex paperwork and shipping requirements and packaging and all of this, and that makes it cheaper to ship as well as to make. But there is a warning for sodium ion. It's not necessarily going to be the holy grail. It depends on the materials that go into them. So I've recently been compiling a report for the UN that looks into the chemical risk of electric vehicle batteries at end of life, particularly in low and middle income countries. We want to try and move away from fluorinated compounds because fluorine, if it's partially decomposed, like for example if the electrolyte salt is partially decomposed or if the PVDF that's used to bind the cathode material to the current collector is partially decomposed, you can end up producing hydrogen fluoride, HF, which is quite nasty. There's other nasty fluorinated compounds that can be produced if it's not properly recycled and dealt with. But that is not an insurmountable issue. If it's properly recycled, it's no problem. But it's like, what if it's not? And so you would typically find fluorinated compounds in the electrolyte salt, lithium hexafluorophosphate, LiPF6, that's in pretty much every lithium-ion battery today. PVDF used in the majority of lithium-ion cells as the binder for the cathode, as I pointed out. And sometimes, just to be annoying, the separator, the plastic separator, might get coated with PVDF, but it's like, why would you do? You don't need to. Anyway, so yeah, now that we're more aware of the nastiness of PFAS, forever chemicals, and so on, we might hopefully move away from that quite quickly. So we're trying to move away and defluorinate our batteries just to make sure that in a worst case scenario there's nothing nasty that enters the environment. And along comes sodium-ion, and your layered oxide cathodes are fine. You've also got your Prussian blue / Prussian white, which is basically used in paint. But yeah, it's super cheap materials. Seemingly quite ethical. The only thing is that if it gets in touch with water, like for example during hydrometallurgical recycling, it can produce cyanide, so you want to make sure that you recycle that responsibly and using means that are set up for sodium-ion cells rather than lithium-ion. But again, this is just looking at absolute worst-case scenarios here. That said, I think fluorine is something like the 13th most common element in the world. And it's also used, of course, in dental care products. It's used in toothpaste and so on. So, it has its uses, but it can also be turned into something nasty if it's mistreated. So that's just something else to keep an eye on. But whilst it's in a battery, it's not going to affect you. It's just, we're talking recycling here and safe disposal.
So what about things like zinc air cells or lithium air cells?
So lithium air cells are actually what I did the first half of my PhD on, and that would have been starting back in 2011 when they were meant to be 5 to 10 years away. And I think that the estimate for how many years away they are has gradually increased ever since. So lithium air is an interesting one in theory, and it makes a very good primary battery, in other words, one that discharges once and you don't recharge afterwards. Secondary battery, bit more of an issue. So what you've got is you've got pure lithium on one side and you've got graphite on the other. And that graphite has a porous membrane on it, which allows oxygen in from the air. Lithium comes across and it forms lithium peroxide or some other kind of lithium oxygen compound. And you're talking substantial increases in energy density versus lithium ion today, minimum 4-fold increase in energy density using very cheap materials. There's a couple of issues. One, you are limited by the rate of diffusion of oxygen from the air into the cell, although that's actually quite good from a safety perspective, because if you short it, you could also just shut off the cell from the air and it would just be limited by how much oxygen it has available to it right now. So, it would very quickly fizzle out. But the other issue is that it has a habit of eating itself, basically. So when you're using organic electrolytes, so that's your kind of oily electrolytes, I suppose, if you want to be crude about it, you end up with those lithium oxygen compounds generally being insoluble. So they kind of stick to the reaction sites within the graphite. And as a result, the cell chokes itself. But also you'll end up with side reactions where these are kind of nibbling away at the electrolyte itself. So you typically end up with a handful of cycles before you've lost a substantial amount of capacity. And one of the first papers I published was on different electrolytes and basically why they don't work. And, it was a modeling exercise by some of our collaborators, and I was doing the kind of physical data gathering and verification of what we were coming up with this model and proving that, electrolytes that have certain very niche qualities about them that I won't bore you with just now are better for use in lithium air, but some of them are a lot worse if they have, the opposite kind of qualities to what you want. And these are the qualities and these are the electrolytes, yada, yada, yada. But something else that happened whilst we were there during my PhD was we discovered that lithium air cells are a bit like whiskey. There is a bell curve of moisture or of water ingress where you end up with like peak performance and then it drops off again. So with whiskey, if it's neat, it's enjoyable, but it's it's not as good as it could be. You add literally 1 or 2 drops of water, wow, it really opens it up. And then if you do what basically the sacrilegious thing and you dilute it with like an entire ice cube or Coke or something inexcusable, it just falls off a cliff. So we had spent all this time trying to remove moisture from oxygen that we were putting, pure oxygen that we were putting into lithium air cells, because we didn't want to have any atmospheric pollutants or anything. We didn't want any side reactions like that. We just wanted to get the fundamental chemistry right. Then, now that we'd proven it worked with pure oxygen, we can start to introduce more air-like qualities to see if there's anything that needs to be toughened up about the chemistry so it can cope in the real world. And we discovered that actually a little bit of moisture improved the performance, improved the lifespan. So fun fact. It remains a long way away. It generally fell out of favour because solid state became in vogue, sodium ion became in vogue, lithium sulfur became in vogue. But there seems to be still some research groups out there plugging away, and potentially with the advent of AI, we might be able to find an electrolyte and material combination that works effectively. We've already seen some research groups using AI to try and find implausible but actually really good electrolyte combinations for more conventional lithium-ion cells. So maybe that could be the savior of lithium air, or it could just be some bright young prodigy who comes into the lab with a good idea and a can-do attitude. But whatever it is, it would be nice to see lithium air reach commercialization. But if it ever does, I expect it will be doing the base load in an electric car / range extending, because it's not a high-performance battery. It's a low and slow, long-range range extender, because the maximum power, as I said, is limited by the amount of oxygen you can stuff into it in quick succession, basically.
And you mentioned there about, some enterprising young person coming in and finding a solution, etc. And of course, that is what allegedly happened with the Donut Labs solid-state battery. It came from nowhere. It was meant to be earth-shattering. It was meant to be bleeding edge. I don't think it turned out that way. Do you have any thoughts about the solid-state to Donut Labs battery?
Yeah, I had my suspicions. I've been on a couple of other podcasts and having done a bit of sleuthing myself, and in wider informal conjunction with a lot of electrochemists on LinkedIn. And yeah, there were a couple of telltale signs that something might not be right, but there was still potentially a glimmer of hope that it could be the real thing. So for a start, people were saying, oh, wow, look, the cell has managed to withstand 100 degrees Celsius. The actual lamination on the pouch cell gave up, it melted, which would have allowed air into the cell. Surely a lithium-ion cell couldn't withstand that. It's really only if you kept it on stupidly high performance for a very long time and then stabbed it with a metal nail or something, that it would have an issue with it. You could have a small amount of air ingress for that amount of time, and a lithium-ion cell is not going to be too annoyed about it, especially because the area of pouch that had failed on the vacuum seal was very small, and it was still fairly shut together. So it's not as if you had a massive fan blowing air into it. So yeah, I wasn't convinced that ruled out liquid electrolyte or a lithium-based chemistry. Where it got interesting was the voltage profile, the discharge voltage versus time or state of charge. And I did some sleuthing with some spec sheets and journal articles and so on. So they claimed it was a non-lithium chemistry, probably sodium. And I took some sodium-ion cells and I took some NMC lithium conventional cells. And I took the discharge voltage profile of the donut battery and I put them side by side. And there was a possibility that it could have been sodium-ion layered oxide. The voltages were very similar. The pattern was fairly similar on the discharge curve, but it was more akin to lithium-ion NMC because there was a telltale hump right at the beginning of the discharge that wasn't there with sodium-ion. But that's not to rule out the possibility that there was some funky sodium-ion chemistry that might have had this same effect within it. But I was still thinking, if anything, the hallmarks are more lithium-ion NMC at this point. And yeah, a few others had pointed out that, for example, although the energy density was never publicly revealed, they had photographs of these cells next to multimeters of a particular make and model. And someone measured the multimeter, used that to measure the cell, and then worked out the energy density and figured out that it wasn't anywhere near what Donut had said it was. So I think they were saying 400 watt hours, so however many 100 watt hours per litre it was, and they calculated, well, actually, it's only this many litres, which translates to only this many watt hours per litre. But yeah, the real giveaway that someone else figured out, and fair play to them, was that they'd actually been given data on the swelling of the cell during charge and discharge. And that was a signature of lithium-ion NMC rather than any kind of sodium-based chemistry. It was like, wow, okay, I missed that. That's good. So yeah, it looks as if it's all been a bit of a charade.
Yeah, and I think somewhere down the line, there's probably going to be lawsuits from various companies. I ran into a guy the other day who has a YouTube channel, and I can't for the life of me remember what it is, but he's the one who went into extreme detail, got the lawyers involved, the whole lot to make sure that they couldn't sue him. Literally ran into him at the BYD flash charging demo. Nice. He was there. We chatted about that for a while. So yeah, he said I was quite clear about what it was, and I had to make sure that I was legally covered because somewhere down the line there's going to be a big lawsuit on this. So interesting. We've taken up quite a lot of your time today. I really do appreciate you coming on and chatting about batteries. I know it's something that you like doing, and I like listening to it, so I appreciate your time.
No problem.
So did you get all that? Certainly knows his stuff, doesn't he? Now, I linked the research paper that he co-authored in the show notes, so you can all have a look if you wish. Or am I the only one who likes to go back and look at the source research? The EV Musings podcast is sponsored by ZapMap, the go-to app for EV drivers to find and pay for public charging with confidence. ZapMap is free to download and use, with thousands of public charge points to choose from, live pricing and availability information, and a range of filters to find the right charge for you. Plus, choose subscription models for enhanced features such as using ZapMap in-car, on CarPlay or Android Auto, and discounted charging across thousands of charge points. But that's our show for today, and I hope you enjoyed listening to it. It was put together this week with the help of Dr. Euan McTurk. His contact details are in the show notes, and I'd like to thank him for his time. If you have any thoughts, comments, criticisms, or other general messages to pass on to me, I can be reached at info@evmusings.com. On the socials, I'm on Blue Sky at evmusings.bsky.social. I'm also on Instagram at evmusings, where I post short videos and podcast extracts regularly. Why not follow me there? Many thanks to everyone who supports me through Patreon on a monthly basis and through coffee.com on an ad hoc one. Regular listeners will know about my 2 ebooks, So You've Gone Electric and So You've Gone Renewable. They're 99p each or equivalent, and you can get them on Amazon. Check out the links in the show notes for more information, as well as a link to my regular EV Musings newsletter and associated articles. Now, my stats show that a lot of people watch this on YouTube, but they're not subscribers. So if you're one of those, why not hit that button and the notification bell so you don't miss out. Thank you very much. If you've reached this part of the podcast and are still listening, thank you. Why not let me know you've got to this point by tweeting me at musingsev.bsky.social with the words solid state, hashtag, if you know, nothing else. And thanks as always to my co-founder Simon. He'd be lost without batteries. He really would. Brings out the pyromaniac in him, which is frustrating with some of the current chemistries out there.
I mean, you can get them to catch fire if you are determined, but I can get my office desk to catch fire if I'm determined.
Thanks for listening. Bye-bye now.